Welcome to
Okay.
Physics with a Bang 2018.
This is the 12th year we've been doing this, and we welcome all of you. I'm Heinrich,
I'm Sid.
and
Hey.
you're here to listen to a
Bang.
Bang.
Are
Okay.
you ready?
Let's have a bang.
Okay. Are you ready?
Careful, ears.
Whoa! Was that a bang? Would you like to see that again?
Would you like another bang? Okay.
Okay, are you ready? Okay, get ready. Whoa! So, one of the things that we have here is you probably got to hear that, but you probably didn't see what went on. And so we've got our two camera operators, Nidhi and Jiayi, who have been able to use a high-speed camera to capture what you just saw.
So here you see what happens. See up there in the corner, that's the balloon. And now the explosion takes place. So this is something we can do with the high-speed videos, and this was 4,000 frames per second played back in slow-mo. This is what you just heard.
Okay, so now we need to get a volunteer to come down and help us with this. Okay, could you come down and help us? Okay, so you'll help Heinrich at this end, trying to light this paper up at that end.
Okay.
You're going to be doing it by working over there.
So you're going to turn this dial really carefully up. Just turn it this way. Careful.
Be careful.
Little bit more, little more. And you can watch. You know there will be a light going on there that starts with a light bulb right over your head.
Right over there, going to a light over there, trying to light that sheet of paper.
Go a little more, a little more, a little more, and see if something will happen. Yeah, careful, careful. Let wait. Okay.
Oh,
Whoa. And here we see that nothing happened. All right.
Oh. So let's
Thank
give him a
you.
hand. So one of the things that you know about, you probably, a lot of you have been on airplanes, and you know what keeps an airplane up. I mean, there are a number of things, but one of them is
The Bernoulli Effect.
the Bernoulli Effect.
Now, what
And
is the Bernoulli Effect?
So if I blow, you would think that I'd blow everything out of the way from where my breath is going. But in the Bernoulli Effect, not only does it blow things out of the way, but it makes the air go faster, which lowers the pressure. So things should go into the place where I'm blowing rather than away from it. So let's see if that works.
Notice he blew
Above the paper, and
the
it goes
paper.
up, the paper rises. But I think that was kind of pathetic, don't you?
Yes,
that wasn't...
I mean, I think that was pretty good, but
But
can
should we
better.
do it industrial style?
Yes.
Okay,
let's do
so
it
industrial style. So here we go. Okay, so now here we go. Air blower above the sheet of paper.
Above the paper.
Above the paper.
And did you see how the thing would fly off? Let's see what else we can.
What else could we do, Heinrich? What, do you have
Fly.
any ideas?
Oh, I have an idea. I have an idea.
Okay, so here we go.
Okay. All right.
Okay, so that was air again, but now we want to do something else. Well, how many of you play musical instrument? Oh, a lot of you play musical instruments, right? And so what do you have to do if you play a musical instrument? You have to get the notes right? That's one thing, but it's not just the notes. You have to get it on the beat. If you don't get it on the beat, it just sounds terrible. And so what you want to do is have the notes and the beat. And so what does your music teacher tell you to do? Get a metronome, and the metronome gives you a very clear, clean beat. And so we have here some metronomes for you to listen to, and so that's what you would hear, right? But if one metronome is good, two should be better, right? So we'll put 2 on. And if 2 are good, then 3, and then 4, 5. Oh, wow, that doesn't sound so good. I can't keep time to something like that. So what I'm going to do instead is I'm going to take that and I'm going to now take these
All of
cans,
them. A whole bunch of them.
and all of them, I'm just going to sit this on top of.
Wait.
Now it's better than 2. And if I put it back on the table again, it's a mess, right? So that just goes to show you that when you're having trouble keeping time, have a little break, have a little refreshment, and you'll be fine.
All right, so that was sound that you heard. Let's see if you can see the sound now.
Okay, so what we have here is a tube in which Heinrich has got the gas going through this tube, and there are little holes at the top through which the gas is coming out, and we've lit them. And so you see a very nice holiday, cheery bunch of candles all lighting up there. And one other thing that we have at this point is a speaker down at this end, so that if we put a tune to that speaker, then we might be able to see what the sound waves are doing inside this speaker, and you can see that visually by what the flames are doing.
It's kind of like playing a flute.
Now, we've also heard something.
Yeah.
What is special about today, Heinrich?
Oh, I think today it's somebody's birthday, or is it almost somebody's birthday? I thought there was something like that.
Is it birthday party? Well, then we should sing.
Sing. All right, why don't we all sing?
Are we all ready?
Yes.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Auburn. Happy birthday to you. Yay!
So that was beautiful. And that was so
Quiet.
festive and quiet.
And nice. And no noise at all, really.
So this is
It's time
physics
for
with a
something
band,
better.
right? We need to do more.
Okay.
Let's use sound to break something. How about we break a real wine glass with sound? Now what we have here is a wine glass, and there are two speakers that will now blast this glass with sound to the point that the glass will start wiggling and eventually breaking. And so that you see what happens, we got the camera aimed at that again. It will break really fast, and so that means we will show you how that happened by playing it back. But first now, we'll just show you what the camera sees.
So this is live.
And as you can imagine, you need a lot of sound to break a glass. So this
And
could
so
be
this is going to be one that
loud.
you're going to have to put your fingers in your ears.
You see how the glass is shaking? It's already feeling something.
Oh! And this is Andrew, who put it all together. Yay, Andrew!
All right, so we will play that back for you in a second. And meanwhile, we're setting up the next experiment. Okay, so here you can see now everything played back in very slow motion. See the wine glass, see the two speakers below, and here we see this thing crack.
Okay, and so now what we want to do is something else with air this time. And what I've done is I've taken some of that liquid, which is alcohol, and I've put it into this big water container. And now I'm twirling it around, and this is going to take a little bit of time, so I have to tell you a story, and so otherwise we'll all be bored. Okay, and so the story that I just want to tell you is about a YouTube video that you can see on the web, and it's about this person who in the middle of winter comes into a gas station to fill their car. And so they get out, they put the gas handle into the outlet, and they, because it's cold, they go back into the car to keep warm. And so they keep warm and they stay there. And then it's about time for the the gas to have all been filled up. So they come out and they make one bad mistake, which is then they reach for the gas handle. And as soon as they touch that gas handle, the whole car bursts into flames. And the reason that burst into flames was, well, while they were in the car, their clothes rubbed against the back of the seat, and they picked up some static electricity. And so then as soon as they touched the gas handle, that spark set off all of these fumes, and this thing then just went to, everything burned up. Now the good thing, end of the story, is that no one was hurt, but it does tell you that you should be careful about flammable gases and any sparks that you might have. And so this is what we're going to try to do, is to show you now what happens if you do that in a more contained situation than that. And so are you ready? Okay. So we've done that in this container. And so now I'm going to try to light this up. Okay, so that's what happens if you're not very careful. So Heinrich is going to be careful, of course, right?
Of course. But I didn't like it this way, right? Where could this poor thing go, this bottle? Why don't we tilt it a little bit? And my idea is to put it this way. See what would happen if we put it that way.
Uh-oh. Hey! Bullseye!
All right.
This is...
Ready? Now, of course, we filmed that, and so let's play this back for you. Here you see how the flame starts at the top and then makes its way into this container, lights everything up, the reaction is going on, and then this flame front is moving back out. And this was done at a high speed of, nothing, just 600 frames a second.
And you can see that as the oxygen gets used up inside, more gas comes in, and this thing keeps going down, up and down, up and down, as this wave of flame comes in. Okay. So now what we have here is a liquid, and this is just an ordinary liquid. And the point about this is that if you look at this, you see that this stick that I'm putting in here looks broken, right? That is, as the stick passes the top of this fluid, it looks like it's just severed in two. And this, is something that you've probably seen before, and it's something having to do with what's called index of refraction of the fluid, and that's different from air, and so it makes the shape of this rod look tilted or broken as it passes from one fluid into another with different index of refraction. So that's one thing that you've seen. And so, what else can we do with this fluid? Well, if I take this out now, I just have a clear container, nothing's in it. And so what can I do? Well, if I have this sign, can anyone read this sign?
Really?
It doesn't look like bang to me. It looks...
How do you do that?
It looks like gnab, but gnab backwards. I don't know how... It's a weird kind of thing. And so what we want to do is see whether you can read it frontwards now. And so if I take this and I bring it through here, you should be able to see through this liquid that it's acting like a lens. And so this lens now not only magnifies it to some extent, but it also reverses it. So the thing that became GNAB backwards becomes BANG in the right direction. And so this is like a lens, and so this is, if you have high quality optics like a microscope or a telescope, you usually have two lenses or more than one, so that the reversal of one lens then is reverted back to the original by the second lens. So you need two lenses to do it. Okay, so this is a nice simple liquid. I said it was normal, but it's actually a magic liquid. And so what I want to show you now is in what way this is magic. And so here is a glass tube, okay? You can all see that it's a glass tube. It's a solid glass tube. Do you all agree it's a glass tube? Okay? Okay, and so now I'm going to stick this into this bag. And I'm going to take this bag, and I'm going to take this hammer.
Oh, no.
And I'm going to take this, and now I'm going to smash it. Okay, so now I'm going to ask you, is this smashed? Is it smashed? You all agree that it's smashed. Okay, so I'm going to take the smashed liquid, the smashed tube, I'm going to stick it into this magic liquid.
See the pieces going in there? This is really
So
smashed.
that's this, all of that is gone in there now, and I'm going to wave my hand around this and see what happens. And now what I want to do is I want to see what this magic liquid did to that tube. And so I'm going to now pull this out and see what we have. Okay, so
Wow.
this, of course, is not a magic liquid. This is just the fact that this tube, remember I told you about index of refraction before? The index of refraction of this liquid is precisely the same as the index of refraction of this tube. So when I stick it in, it becomes invisible, and you can't see it anymore. So this was hanging in there all the time, and the glass shards are still in there, and I'm not going to take them out with my hand to show you that. Okay, so that's so that's. Okay, so there's something else that I can do with this fluid, and it shows the power of science and the power of physics. Okay, and so what I'm going to do is I'm going to try to reverse time for you here. And so what we have here is we have a cylinder on the outside, and you can see through that cylinder. And on the inside, I have a piece of white plastic cylinder, and so that's white. And I can stir the inner tube by just turning this around, and that turns the inner cylinder, leaving this one fixed. And so there's fluid between the inner cylinder and the outer one. Okay, and so now you can all see that that gets mixed up, right? No, because you can't see the fluid, right? So I have to do something so that we can see where the fluid is in order to see that that gets mixed up.
And by the way, this is the same fluid that we were just seeing in that jar there.
Special fluid that. And so what I'm going to do now is I'm going to put some dye in here so you can see what's happening in the fluid. Okay, so I'm going to start off. So that's an S. It stands for science, right? So S is good for science, and we can never destroy science, right? Because science is real and fundamental and cannot be broken. And so I'm going to stir this and nothing's going to happen, right? So I'm going to stir this. Uh-oh, Heinrich, it disappeared.
What happened to science?
Science seems to have disappeared. Okay, so now we'll try and see whether maybe physics is stronger than science. And so we're going to put some, I'll try and put in a P here for physics. Okay, so.
Can you all see it?
Okay, so that's the P for physics. So let's see if physics can withstand.
Turn it so that they also see. I mean, we're really putting a P in.
So
This
can you
is
see?
very
Can you all
important.
see the P now? You all see the P. Okay. So now I'm going to stir this and see if physics remains.
Oh, physics is all
Oh yeah,
stirred up.
yeah. Physics disappeared as well. So I guess let's just keep stirring this. But I have faith in physics and I have faith in science, and let's see what happens. So I keep turning this, and so maybe I should just keep turning this. So let's keep turning it. 1, 2, 3, 4.
Whoa.
Oh, so physics was powerful after all. You're able to reverse time. Okay.
Sid, what about science?
Oh, do you think science is also going to be survived? So let's keep turning and see what happens. So there is science and physics all together. And so, of course, we didn't do anything funny here. This was just an illustration of what turns out to be a theorem in fluid mechanics, which says if we make a very specially made vessel that I'm able to reverse all of the boundary conditions, it comes back exactly to where it was. And so that's all that we've done in this case.
So that was a liquid that was not water, obviously, but it was a little thicker. It was glycerol. And now let's see what else we can do with a liquid when we make it a little thicker. In this case, it's made a little thicker by putting small particles in. These are tiny little particles that you even have at home. So this is cornstarch, but look, it's a liquid, right? See that? So the question is, can I jump onto that liquid? I don't know. Do you think I can walk on water with little particles in there? Oh, I don't know. So I should just jump right in there, right? Okay. Look at that.
He can walk on water. He's pretty good.
Can just walk over that. Now, you think that it's not a liquid, right? Let me just show you. What if I just stand there for a little bit? See? I'm sinking in. This is really a liquid, and it is a crazy liquid.
Whoa, Heinrich, you're going to get wet.
Because if I want to get out, I have a hard time. See? It's very hard. So what else can this liquid do, Sid? What do you think?
Well, I wonder what would happen if you drop something into that liquid.
Ah, that's a special liquid. Let's drop something in
Is that a good
there.
idea?
It's a great idea.
Okay, so here he has some more of that liquid, and he's going to get into this contraption and try to lift himself up.
Yeah, because I don't want to throw it just like this. Let's make it more fun. Let's drop it from higher. But actually, you know what? Let's drop something that is a little bit more fragile. Don't you think?
Yeah, well, he said jump in it, but I don't think that's nice.
We did
I mean,
that. That's
but
okay.
but we can do something gentle, fragile.
Gentle, fragile. What is fragile?
An egg! Oh, great idea. Do you happen to have an egg there?
Oh, I think I found one right here in the corner.
Oh, excellent.
Should we drop an egg in there? Now this liquid is special because if I drop that on the floor, you know what would happen, right? But look at this. Ah!
Oh, you
I
hit
hit
the
the
side.
corner.
You hit the side of this, Heinrich.
I hit the side of it.
Do you have another egg?
No, I think we need to do something different. That was easy. Eggs always crash, right? Let's do something more complicated.
How about a bowling ball?
Okay. How about a bowling ball?
Higher, Heinrich. Oh, is this going to come over us?
I'm really afraid of heights,
Aren't you
know?
worried?
Okay.
Oh, you're
okay.
not going to be worried. Oh, that way.
That's really high. Okay. Now you guys there, you know, you're going to get all wet. You know that, right? Okay. 3, 2, 1. Oh! Look at that. It didn't even splash.
Heinrich, we have an egg now. Do you want an egg?
Okay, let's do the egg. All right. Higher, good. Okay. Egg, egg,
Egg, egg, egg.
see? It is beautifully alive still.
Look at that. It didn't break at all. But now, how many of you think that this was really a hard-boiled egg? Yeah, it was really a hard-boiled egg. Okay, so can I have some help over here? Would you help me come down here? And so we're going to try and see if there's a hard-boiled egg. So I'd like you to just take this and hit it against the wall. So, but don't throw it too hard, but
Just throw it. Yes.
This indeed was a raw egg. So thank you very much. Can I have it? Okay, so now we'd like to do something else with air, and I need another volunteer. Let's see. How about you from up there? Yeah, yeah, there. Good. Okay, and so what we need from you is to make sure that we are being honest. Okay, can you make sure that we're being honest? Okay, so what we're going to try and do is we're going to try to float a boat. Okay, so this is a boat, right? It's obviously a boat because it says boat, right? But we're going to do this. I mean, it's easy enough to float a boat on water, but I want you to just check in here and see there is no water in there, right? And now I'm going to try and fill this in with, there's gas coming in here, but there's no liquid, right? There's just
sure.
gas. So this is correct?
Yes.
She says yes. Okay, so this is really nothing. We're not doing anything funny with any liquid in here. So Heinz, would you help me remove this
Okay.
this very carefully? Okay. Okay, and now could you just double check that there's no liquid in there? Okay, no liquid, right? So now we're going to try and take this boat and see if it floats. Oh, what do you think of that? So this is floating pretty well. We can drop it in there and it just floats. Just because this gas that we put in here is a particularly heavy gas. It's called sulfur hexafluoride, and it's much heavier than air, so it's in this container, and this boat can float between this gas below and the air above. And now I'm going to try and sink this. So we... There it goes. So thank you very much. Let's give her a hand.
Now the thing about gases, like you just saw, is that you can't see them, right? But you can notice something about gases. You can hear me talk right now, and you can feel wind that goes also through the air, right? You feel that, right? You can feel that too. But can you see it? No. So we put some smoke in here, and then we want to show you what happens. And now you can see it also here. Okay, thank you.
Okay, are you ready?
Are you ready for some fun? It's enough, it's enough. But the whole room is. All right. So something about air is, of course, it transmits sound, but it also changes when it changes temperature. And you know that when you are in the summer and you look over a road that is hot, or you look towards the horizon over some hot soil, there's some shimmering in the air, right? And that's that index of refraction again. Something about the air changed because of temperature. And this is very subtle change, but we can make that visible with the setup that we have right here. And so we need another volunteer, right?
And we'd like a volunteer from this side this time. Okay, would you come? Yeah, you. Oh, okay. Yeah, you in back. Okay, yeah. Or you can both come. You can both come down. Both of you come down. We need both of you. Yeah, you too. Okay, so what we're going to try to do is see if you are, whether you're warm or whether you're cold. Okay, so what we're going to do is we're going to stick our hand right here. So let me do it first, and see that. You see the heat that's coming off my hand. It starts to shimmer. And so now what we'd like to do is see if you put your hand right there. Oh, look at all this. You're alive. This is great. Maybe you want to see if you're alive too. We'll put it over here, close to this. Yeah, you're both alive. There's one, and not only you're alive, you're warm-blooded animals. This is wonderful. Congratulations. This is great. And so we're going to show other things too that you can do. So if we take this. Well, you can see the gas coming out of this.
And the heat. You see the heat too.
There. And now you can see the heat come up off of that. And now one other thing that you can see is if we take this. So this is very cold. So this is dry ice. And now you can see that the cool comes off of it. And so instead of having the heat rise, we're seeing cold air drop down below this. And so you can see how that works. Okay? So let's give them both a hand for being so good. And so thank you very much.
So Sid, that was really very beautiful, very pretty, but we know we need to crank up the danger level a little bit.
Danger level?
Danger.
Uh-oh.
This is physics with a bang after all.
Okay.
And I think, we want to try something with the bowling ball.
Uh-oh, so you're asking me to be dangerous.
Yes.
I'm the one who's got, okay, we'll try this out. Okay, so what we have here is we have a bowling ball on a wire coming from the ceiling. So this is a pendulum that'll go back and forth, okay? And so what we know about this is that certainly if you start this at some height here, it'll never come back to higher than that height, or we hope so, right? That's what we're aiming for. Okay, so we want to show that, and so we're going to show that we have an egg right here, okay? So, and I'm going to put this up next to the egg. So certainly if this goes any higher than it starts, it'll break the egg. And so this is going to show you that this certainly could not break the egg, right? So we're going to start this here.
Okay.
And
Let's
so this
see
is going
the
to be
test.
fine. Oh my goodness. So,
Sid, I don't know.
well,
Something is wrong here.
physics works most of the time. And so, and it certainly isn't going to fail twice in a row, right? That would never happen. And so,
But how do you want to test that?
So, well, we're out of eggs, and so I have a nose.
There.
So we're going to try
That's
my
it.
nose and see whether I can keep my nose intact. So I'm going to stick my head against the wall so that I can't move my head backwards, right? And
Yeah.
I'm starting this at my nose, and my nose can also not run away. It can run but not run away. Okay,
Yeah.
and so here we go. I'm going to start this off, and it's right at my nose. Is it right at my nose? Oh yeah. Okay, so here it goes.
Okay. Sid, I don't know if that's a good idea.
Oh,
Have you
no.
thought about that?
So clearly, In case of those of you who didn't know, I mean, physics actually works all of the time, not just part of the time. And what happened in the first time was I gave an extra little push. And that's why I came back and smashed the egg. And I was very careful the second time when my nose was on the line, I didn't give it an extra push. Okay, and so that's the... so
All right.
now we're going to do something very, very, very quiet, okay? So be careful and make sure that you're ready to put your
Yeah, this is our
fingers in your ears.
Our quietest experiment. Do you know what this is? Yes. Do you know what's in there? Do you know what happens when it comes out? No?
It's going to be very loud.
Are you sure? Okay, you're warned. You're warned. Okay?
Oh, God. It seems we have a bit of a problem, and so what we're going to do is we're going to ask Jai and Didi to help out for a while we take Heinrich to the hospital. So here you go. Could you take this? And so we will try to be back, but you're in good hands.
Hi everyone. So let's see what we can do here while Heinrich and Sid are away.
Okay. Okay, so what do we have here?
I have a copper tube over here. As you can all see, it's hollow. What do you have, Jai?
Oh, I have a copper block.
Oh, okay. Well, what can we do with this?
Can I put my copper block into your copper tubes?
Sure, it's a tube. It will fall through. I don't think that's interesting to anyone.
Let's try it.
Okay.
Oh,
Oh, well, the tube is hollow. Yeah. Do you have anything else?
I have a magnetic one.
Well, copper is not magnetic, so I think it will do the same thing. It's not going to stick to the copper tube.
I bet not.
Okay, let's see what happens. Oh, it's actually inside. It's falling really slowly.
Is it disappeared?
No, it's in here.
What happened? Ooh.
Oh. Wow, yeah, that took really long. So what do you think was going on there?
So this copper tube create a current that hold this magnetic block and prevent it fall. So that's what happened.
You think that's because copper is a conductor?
What is a conductor? You mean a music conductor?
No, not that kind of conductor.
Oh, a train conductor.
No, I mean a conductor of electricity, something that lets electrons flow through it. So copper is a good conductor of electricity.
Oh, so copper is a good conductor of electricity.
Right.
So now we have superconductor here.
Oh yeah, so superconductors are materials that are really good conductors of electricity. They have absolutely no resistance, and we have these crystals that become superconductors once you cool them in liquid nitrogen. So what we have here is a container with pieces of superconductor, and we'll add some liquid nitrogen in it to cool it down.
So in here we have a magnetic rail. It's like a train rail. So what are you going to do with it?
I think if you put the superconductor on top of the rail, it will float there.
Really?
Yeah.
Let's try it.
So this is a piece of superconductor. And yeah. See, it floats.
Ooh. Wow.
Yeah.
It's not floating? I can put the paper in here.
Yeah, it really is floating.
Can I put this upside down?
I wouldn't do that. It's heavy and it might break.
Okay.
But there's another rail over here. Maybe you can put it under this rail.
Okay.
Do you think it will float?
So I have another one here. Now I'm going to put it upside down.
Whoa. Oh, that's interesting.
Oh, see who's
Oh.
back.
Oh, well, thank you so much for saving the day.
Yeah.
All right.
Okay.
Anything for science. So, Nidhi,
Would you like to listen to some music?
let,
I'd love to hear some music because I think
let's have some music.
you know, he's been under a hard strain going to the hospital and all of this. It's time for some music.
Let's listen to some music. Oh, good. Oh. I broke it.
Heinrich, why did you break it?
It was open. I mean, I thought I had to pull on it.
Well,
Well, let's see if we can conduct this sound through more than two people. How about we go all the way this row here? Yeah, this row. Can you all hold hands? No, you have to hold hands along the row. Which row? Okay, keep holding hands. All right, okay. So now can you touch me? Here, somewhere. Okay, now touch here. That's much better. Come on. Take it off. And more. See, it works. Electricity.
so this is one lesson. This is why you don't want to have electrical things in the bath with you.
No, this was totally harmless. See? But that was really only very little electricity. The electricity you have in your iPhones, that gets into your speakers or your ear pods. So why don't we go to a little bit more electricity now, Sid? What do you think? We just go
Oh.
to a couple 100,000 volts.
Okay, so I guess we should do this, right? So we're going to try to charge this up, and okay. So why don't you
All
turn
right.
this on, and let's see what happens. Wow, that's pretty good. If you turn the light up just a little bit more, you can see that I have great power here. I just point this thing, and it stops sparking. So this is the principle of Benjamin Franklin's lightning rod, that a sharp point pointed at the sky will bleed out all of the electrical charge that's accumulating on the clouds, and we can see that here. So here we have these beautiful large sparks. Let's see if we can get a larger spark. How big can we make that spark? So we can get really nice sparks. Can make it stop, go, stop, go. Okay, so let's
That
see
was
what
kinda
else we
nice.
can do.
Can you light up something without even touching?
Okay,
the
so I'm
electricity?
going to try to light up a light bulb, okay? And notice I have nothing up my sleeves, okay? So no electrical wires anywhere. And I'm just going to hold this, and we're going to see if I can't get the force, okay? So Let's try this, Heinrich. Let's go.
All right. Very
So,
nice.
may the force be with me.
So now my colleague is going to undergo a little transformation. Just wait here. And we're going to do the death-defying stunt now. He will be electrified. Voila!
Okay, Heinrich. So let's see what we can do. I'm going to try and get up on this thing and charge myself up.
That's right.
Okay.
You go right ahead.
But maybe we should get this down.
We
and
go
I'm
for
going
the
to try
biggest
and
of
get.
sparks.
I'm going to get up here. Oh, I have to do a couple of things. One is, one time I did this, and I started getting shocks between my eyeballs and my glasses, and that was very upsetting. And I had the machine operator to please turn it off very quickly, and so I have to get rid of that. And also, just the other day, I was trying this, and I started getting shocks between this and me, and I didn't like that either. So, if you could hold that.
What about your ear muffs there?
That's okay. There's no matter there. I don't care. Okay. Okay. So, beam me up, Scotty.
All right, here we go. Don't you like his new hairstyle? Yes, there we go. All right. I think it's a little frizzy
How do I
still.
get down?
First, it's too frizzy. Let's change that. There, see?
Okay. That
Okay.
feels much better.
Now you can go down.
Okay. Thank you so much.
So talking about electricity, right? This was a couple 100,000 volts, very small current. Now we're going to up the danger level considerably. We go lower in voltage, but just do some gigantic current. And what we're going to do is basically equivalent. Have you ever put a screwdriver across a car battery? You should never do that. So here we put a screwdriver, so to speak, across a 9,000 volt battery. That's those things here, those metal cans. And then we run current through a loop. And inside that loop, I have a can here, just a beverage can. And the idea is that there's enough current and magnetic field to cut a beverage can into two.
I don't believe it. Can you do that?
I will have to try it.
Okay.
So this will happen obviously really fast. And so we want to film it. Going to wait until that's set up. And the other thing is, cutting a can really fast could also be really loud, so be warned.
And you want your shield.
Yeah, and also in case something starts flying, not just this way, but, well, that's a shield. You won't get anything, but I already got a bandage here. Maybe I'll be a little safer. All right.
Okay, so be ready for.
Are you ready? So I will call out where we are with the voltage here. Again, these metal canisters here are like big batteries. We are now at 2,000 volts, big capacitors. You want more?
Yes.
3,000. Who wants more? 4.
More.
Okay, you have 6. We're going to 6 now. You got 6. Anybody wants more?
More.
7. Okay. Who wants 8? Okay, we are at 8, and now? Nope, 9. We're going to 9. 9 is it.
That sounds pretty good.
All right, so are you ready? 3, 2, 1.
Whoa. So this is what happened to that can. It got squeezed in the middle, and it got ripped apart, and it's really quite warm. Okay, so and the other side did the same thing. It just squeezed in and pulled itself apart just because of the currents on the outside of the can.
All right, so let's see if we can play that back for you. Again, this is something that you only see here because we got our research grade cameras and this wonderful camera crew. These cameras, they actually can go to way more frames per second, but we have to find it in somewhere in memory where that special moment was, where this thing broke apart, and that's coming up any second now. Are we ready? Good. Hang on 1 second, Nidhi. I want to go to Zoom here. Here we go. So you should see a flash of light, and then how this thing breaks apart. Right, so the current generates a magnetic field, which generates more current, and the whole thing just can't take it and collapses.
So I don't know, these days I'm feeling under such high pressure. Do you feel under high pressure, Heinrich?
I do.
So how come, under all this pressure that we are, how come we're still able to walk around and not collapse?
I don't know. I also feel hot.
Yeah, it's hot and under high pressure. So what keeps you from squeezing in to nothing?
Look, the trick is to balance pressure.
Balance, great idea. So if you have as much pressure on the inside as you have on the outside, then I guess nothing happens.
That's right. Under how much pressure are you right now? You are under tremendous pressure. You're under 15 pounds per square inch. Look at a little square
this
inch.
this is a square inch, and you've got 15 pounds on you from the atmosphere outside on every bit of your body that's doing that. So that means you really are under a lot of pressure.
Thank goodness you're balanced by some pressure on the inside, right? But what if we got rid of the inside pressure? So that's what we're going to do here.
Let's try. Okay, and so what we have here, this is a big industrial style oil drum. Big thing, it's reinforced.
Okay.
So this baby is not going to do anything, right? It's just going to withstand any pressure that we put on from the outside.
And I'm just pumping the air out with this thing here on the inside,
Yeah.
right?
So
So now, see? But, nice reinforcement. Nicely reinforced.
And so it's not going to do anything, right?
I mean, there's a little reaction to pressure like you and I would have, but the thing is industrial strength, isn't it? Nice, big, strong steel drum. But remember, it's 15 pounds per square inch. You have to ask yourself how many square inches that is, right? So
But it's reinforced.
that's true.
Well, maybe nothing's going to happen.
Maybe not.
Okay, so maybe we should go on. What do you think?
Yeah.
Yeah, okay, so let's go on to the next one and
All right.
chalk this one up to experience.
All right. Oh
Okay.
my God.
So here, this was an oil can, and now it's a piece of sculpture. Okay, so this is now something you could display in your living room.
So we're basically doing the same thing again for you, but in a slightly different version. So what we're going to have here is another tube that's now really thick tube. It's also much less of a diameter than the can you just saw. So we know this will not collapse. And then we have the ends sealed off with some fairly thick aluminum foil, which is a few square inches, but aluminum foil can take the pressure across a few square inches, so we can evacuate that whole thing very nicely and nothing will collapse.
We hope. But what we're going to try to do with this tube is at this end, there's a ping pong ball. And a ping pong ball is pretty simple, right? There's not much mass here. Nothing's going to happen with a ping pong ball. But what we're going to try to do with this ping pong ball is we're going to try and get it into one of these cans inside the can. Okay, so do you believe that we can get a ping pong ball inside a soda can? Okay, so that's our attempt. That's what we're going to try to do for you this time.
And the way we're going to do that is we're going to evacuate this tube so there's no air in there, lots of pressure on the outside, and we let the pressure rush in from this side, push the ping pong ball to about the speed of sound out the other way, and maybe into that Coke can. So, as you can imagine, this all is really quiet.
Okay, and so when this goes, it will make a loud pop. But at the moment, nothing's happening because you have it in, we're going to try and film this as well. And so he's going to turn on the vacuum pump. I'm going to read the pressure over here. Okay, and so he's opening the tube. It's 5, 10,
He's reading vacuum.
15, 20, 25, 26, 27, 28, 29, 'Okay, well, it's 30 now. Right. So I guess we're ready to try and see what happens to this thing.
Well, I think we should get all the air out so that more stuff can rush in.
Okay.
But now it's probably pretty good.
Well, let's give it a few more seconds just to make sure that we're.
And I have this contraption here. I could use my finger, right? But I don't want to. So I just puncture it with this little steel bar here.
Okay. And when he's ready to do that, then we put our fingers in our ears, okay? So that it.
All right. So here we go. 3, 2, 1. Whoa!
So this ping pong ball, this little bitty ping pong ball, was able to go completely through this tin can, right? And so this can is a can that was. It is no longer capable of holding any fluid, right? And so we said we wanted to get it in there. We did get it in there for just a bit, and then it came out again. And so Nidhi will show us how it went.
Oh, wait, Nidhi, wait. I want to make this here a little bigger. One more. Oh, no, that's too big. This may be okay. Is that all right? Yeah. So you see the ping pong ball coming from the right, and here we go. Right into the can. In fact, through the can. Bam. Even crumpled the next one. So now, this was a very, very fast ping pong ball, and we had to go with 25,000 frames a second to capture that.
Okay, so I don't know about you, Heinrich, but I'm getting a little hot and a little thirsty.
Okay.
So I think we should pour ourselves something nice and cool to drink.
How about some liquid nitrogen?
Oh, liquid nitrogen, that would be good. So let's try some liquid nitrogen and see. So we're going to try and put liquid nitrogen into this soda can and then see what happens, okay? So here we go.
Now, you guys, you gotta possibly,
Maybe we should get them all.
yeah, move out of the way. Can you do me a favor? Everyone in the front row, just sit up on the stairs, please.
Yeah. Okay, so let's see.
No, up.
Is this enough? No. More. Is this enough? No.
More.
More. I think we need a little more. They're calling for more.
Okay, if they want more, we give them more.
I think just a little bit more.
Good. Let's have a little bit more. How's that?
Oh, I think that's a little too much.
Uh-oh.
Okay, so that's about right. Okay, so now
What we're going to do is we take that lovely drink.
and we're going to take it over here. And now I'm going to seal this up
Really tight.
really tight. And now I get out of there.
And now we wait.
Okay, so before we end, we really want to thank all the people who have helped make this show a success and put it together. So you have seen them back and forth all afternoon. Andrew Nadelman and Brent Barker
Right
with the
here.
demo prep and helped make this all work. Our high-speed cameras were operated by Nidhi Pashini and Jiayi Wu. Our audiovisual crew, who we can't see but has been making everything look good for us, Stephen Bandick, Warren Friedel, Chris Kielch, and Trey Peralta. I hope you've all had a chance to go to the open house. If not, that you should go to it after the show.
Yeah, right after the show, right outside, there will be tours. See us scientists in our natural habitat next door.
And so this is the open house. It was put together by Sarah King, Justin Driller, Eileen Shu, and Jeffrey Gustafson. Our staff photographer was Kai To. And there were about 90 scientists who were volunteers to help make everything a success today. And so it was a big effort by all of them. And of course, we had monetary support from a lot of different organizations, the Department of Physics here, the James Franck Institute, the MERSEC, our Materials Center, and our Vice Presidents for Research. And so we thank all of them.
All right? And now we want to thank you for coming here and enjoying this, I hope, and for going on the tours next. But we want to say thank you in style. And now let's see how we do that.
Wait a minute.
All right.
Okay, so are we ready to do it in style?
Are we doing it in style? Okay?
1,
2,
2, 3.
Okay. All right, all right, all right. Hey. Uh-oh. 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 Where's Sid? Where did Sid go?
Here I am.
There he is. Look at Sid.